What's written on your program today. What I'm going to talk about is basically a diagrammatic calculation that I'm working on with Cindy Keeler to work on finite size corrections to the Bethe Ansatz in n equals 4 super Yang mills. I don't know how to do this without having that appear. So basically we start with what we know, which is the form of the Bethe Ansatz today. We know that integrability should give the anomalous dimensions for long operators in terms of this Bethe Ansatz, where impurities move along a spin chain. They interact via an S matrix, and they carry some momentum. The energy of the whole system, which is the anomalous dimension, is just the energy of individual impurities. And the expansion in lambda of this form gives you the loop expansion in terms of the gauge theory of the anomalous dimensions. The S matrix is split, as we know, into two parts. The first part is the dressing phase, and the second part is just a group theoretic tensor structure. And the interactions, basically at each loop order, the interactions increase in length, so that at the loop order in, the interactions are n-sites long. So this we know and we like. And there's a proposed S matrix which has been proven consistent with various fairly rigorous gauge theory calculations, including for-loop cusp anomalous dimension calculations and for-loop dressing phase calculations, explicit gauge theory calculations that have verified this ansatz. However, we think that this ansatz can break down when the operator length is smaller than the loop order. The interaction range is then larger than the size of the system, so we can't really get asymptotically free states on the spin chain. And if in that case you expect there should be more information than just the S matrix that is necessary to solve the problem. Well, that's a heuristic explanation, but also we'll see that there is explicit differences in terms of the diagrams that you need to calculate that contribute to the anomalous dimension. So if you want to calculate a dilatation operator in the gauge theory, you expand it in terms of lambda. The first part, I'm in the SU2 sector, so the first part is just the length of the operator. The classical dimension. And then the higher parts are calculated by requiring that an endpoint function is finite after renormalization. And then the anomalous dimension is calculated dependent on this renormalization matrix. So at one loop, we have three very nice types of diagrams that show up, and you have to sum over all possible locations in the operator where these diagrams can come in. And this is very nice, and you can calculate your one-loop anomalous dimension. At two loops, life gets a little bit more complicated because in addition to there being a large number of two-loop diagrams, there are also some diagrams which are basically a product of a one-loop diagram times a one-loop counterterm. But you can see the counterterms, you can kind of pair them with the original two-loop diagrams and match them up, and it's not so bad. But suppose you consider for-loop diagrams and you think about if your operator is length 4 or if your operator is longer than length 4. Well, one of the many diagrams that shows up at for loops for long operators would be something that looks like this. But this diagram simply doesn't exist when you're talking about a length 4 operator. Instead, you get a variety of diagrams that you might draw like this that are wrapped around the operator. And these are fundamentally different diagrams that represent different integrals. So the diagrams that contribute to the anomalous dimension matrix change. So you expect that the Bethe Ansatz, which is based on these, might break down. So the basic idea of what we would like to do is consider up to L loops the dilatation operator and say, well, if the operator's length is L plus 1, then the dilatation operator is basically a solved problem by the beta ansatz. It's a exactly diagonalizable Hamiltonian. And then we say, well, consider the change from length L plus 1 to L as some perturbation on this, and try to calculate the first correction due to this change to the dilatation operator, and think of it as a perturbation. Well, so let's phrase this explicitly. We write the dilatation operator expanded up to L loops acting on an L plus 1 operator. And it's some sum of terms that come from diagrams that don't really change, diagrams that appear, for example, the one-loop diagrams that appear regardless, and even some L-loop diagrams appear regardless of whether you're looking at L plus 1 or L. And then you have some diagrams that are going to disappear. Then you write the same thing for the dilatation operator acting on length L. You have the same term, only summed over one less site here. And then over here you have your new diagrams, your wrapping diagrams. So to make our lives easy, we start by assuming that we're just going to look at an operator with two impurities. So the expectation value of this dilatation operator is given by the beta ansatz. And the idea is then to calculate these diagrams and these diagrams specifically. And this and this should give you this part. And then assume that this Hamiltonian that's based just on diagrams that don't change can be analytically continued from L plus 1 to L. And then analytically continue that part. Then you also calculate this, and that gives you, finally, just the first correction to the dilatation operator acting on the length L operator up to loop L. So this is basically perturbation theory, with the slight difference that when you learn perturbation theory in undergraduate quantum mechanics, you don't typically allow your perturbation to change your Hilbert space. But this is really what we're doing when we change the length of the spin chain. So that's why I insist always on working in terms of these expectation values, because it's a little bit messy in terms of the perturbation theory. So to do this for general L is a pretty hard problem. So we'd like to start by trying for the lowest non-trivial length in the SU2 sector. And that's basically the mixing of trace x1, x2, x1, x2, and trace x1 squared, x2 squared. So basically we end up looking for the for-loop anomalous dimension of the Konishi operator in the SU2 sector. Well, there's a lot that's been done on this. There's a 3-loop calculation, there's 2-loop and 1-loop obviously, and there's also a proposal for what this should be. So the first thing we want to do is ask, what are these wrapped diagrams that we need to calculate? Well, they're going to be basically of this type with 4 interactions, one at each sort of horizontal location. That way we involve all of the lines and we end up with a wrapped diagram. Each interaction can be a scalar vertex or a gluon exchange. Then we also have to allow for all possible vertical orderings of these interactions. So with the scalars, there's 2, and with the gluons, there's 3 possibles. And then you can describe each diagram in terms of sort of a word, where there are 4 letters that represent whether it's a scalar or a gluon interaction, and then 4 letters that give you the order of the interactions. And basically, all the possible words of this type will give you all the possible wrapping interactions, except for 3 fermion loops that you can also build. Now, each of these diagrams has a tensor structure that acts on the indices of a length 4 operator. And in the usual spin chain language of doing this, we would think, well, from each x interaction comes a 2p minus I, where pij switches the fields at the ith and jth site. From each gluon interaction just comes a factor of I, because the gluon doesn't change the scalar SO6 or SU2 charge. And then the vertical ordering of which interaction happens first gives you the ordering of the p's in the product. So for example, it's convenient to write these diagrams in terms of sums of diagrams that are rotationally sent to each other. This particular sum, which only involves one scalar interaction, ends up just being proportional to the sum from I equals 1 to 4 of 2p minus I. But what we'd really want to do is relate these tensor structures to the 2x2 matrix that acts on the two operators that we're mixing in this sector trace. And when you do that, you find that each one of these forms of permutation things ends up either equivalent to the identity or some other matrix. And you learn these things, and then you can equivalate to each diagram. You can equivalate factors of M in the identity. Well, there's only two of them, and this is basically just a reflection of the fact that the dilatation operator acting on the Konishi operator is an eigenstate of the dilatation operator, and really the only unknown is the eigenvalue. So how many diagrams are we talking about here? Well, you can do the simple combinatorics, and what you find naively is 433 diagrams, and you think, well, perhaps I don't really need to know the for-loop anomalous dimension for the Konishi operator. But the first thing you realize is that you can redefine the wrapped part and the unwrapped part and the part that's left alone so that they independently vanish on BPS states. And this is consistent with the analytic continuation of H naught. And this allows that you only really need to figure out the terms proportional to M, and then the factor of the identity comes along for the ride. So then you can ignore all of these guys. And it turns out you can also ignore all of these guys because their tensor structure happens coincidentally to just be proportional to the identity. So that gets rid of a fair amount, and now you're left with 256. And then you say, well, but actually not all of these words represent different integrals. Some of these words represent the same integrals, because if a word is rotationally related to another, or if it's reflectionally related to another, the actual diagram you draw on the paper is the same, and the integrals you have to compute are the same. So you carefully work out which ones of these are equivalent to which others, and when the smoke clears, you find that really there are only 42 diagrams that you need, which is still kind of a bad number, but it's definitely a lot better than 433. Now, the only caveat is that when I say diagram, what I really mean is the diagram plus its associated daughter diagrams involving counterterms. So you can associate to this diagram, which is a 3-loop times a 1-loop counterterm, and this one, which is a 2-loop times a 2-loop counterterm, and this one. And it's convenient to work in terms of these sums because when you add a diagram plus all of its daughter diagrams, the divergent parts of the sum are independent of the incoming momenta that you used. And that is very convenient and nice to work in terms of that. So basically, you're allowed to choose your incoming momenta to make the integrals maximally easy as long as you make sure that you haven't introduced any IR divergences into the integrals. So we want to calculate the wrapping Hamiltonian. And it turns out that this requires the following sum of the 42 diagrams. Well, these are the ones that are done. I think this comes to around 20 now. And that's nice. And then there are a couple more that I can do, but only numerically. It turns out that sometimes when you reduce these to master integrals, the master integrals just aren't known analytically, and you have to do some sort of numerical expansion. And in this particular case, I've got a couple here that I can't do analytically, but I have high hopes for eventually being able to find a way to do them analytically, particularly this one. I'm pretty sure I can do that one. And this one I'm working on right now. My computer's calculating it as we speak. Okay, so I'd like to discuss one of the important issues that comes from this calculation is the transidentality of this term. We know that for long operators up to 3 loops, the anomalous dimensions are rational. And at 4 loops, well, yeah, the anomalous dimension matrix is rational, the actual. At 4 loops, for L greater than 4 but finite, we know that any transcendentality comes from the dressing phase, and in particular, the dressing phase contributes terms that have zeta 3s in them, so that the maximum degree of transcendentality for these long operators is 3. And this, of course, has been checked by explicit gauge theory calculation. But consider just one of those 42 diagrams for L equals 4. This is XU, 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 which is basically the first one you write down. And what you find, it also happens to be convenient because there are no associated daughter diagrams. What you find is that the calculation of this involves the zeta 5, which is higher degree of transcendentality. Now, it's possible, and this is not unique. Many of the diagrams that you calculate have zeta 5 in them. So it's possible that this term cancels against the other diagrams in the calculation. And when the smoke clears, we will still have transcendentality degree of 3. However, this is not how it worked for the unwrapped diagrams. In the calculation that Roybon and McLaughlin and Bizert did, the diagrams they calculated just never had zeta 5 in them. They just only had zeta 3 in them. So, on the other hand, maybe this extra transcendentality won't cancel. So I put this as a conjecture, but really it's a question. It's almost the central question to what I'm doing right now. Is this higher degree of transcendentality going to cancel or not? Then, of course, if you have the wrapped diagrams, you need the unwrapped diagrams. I haven't started calculating these, but they tend to be of the form with 4 interactions and 3 ordering letters. The naive calculation is 187 diagrams. You can ignore the 4 gluon diagrams because those are proportional to the identity. And then you can cut in half based on reflection symmetry. And you end up with 80 diagrams. In fact, 47 of them basically take 5 minutes each. 47 of them are very easy because they're based on their 4 basic scalar diagrams, and 2 of them are easy and 2 of them are hard. And the 2 easy scalar diagrams all have versions with gluons replaced, and these aren't really any harder. So those 47 are basically, you can write them off. And in general, we don't expect that these diagrams are easier than the wrap diagrams. So you expect that if you can do the 42 wrap diagrams, this won't present too big of a problem either. So then I just want to talk about the future. Obviously, my short-term goal is to finish calculating these wrapping diagrams. And with that, to confirm or reject the increased transcendentality. Then the next thing to do is to calculate these unwrapped diagrams and finally to put it together with the Bethe ansatz to calculate the correction to the anomalous dimension for the Kanishi operator. And these are, of course, all 4 things that I genuinely expect to do. Now, the next goal is to find some way to generalize these results. Okay. To find some way to generalize these results to arbitrary length. Now, some of the diagrams that you run across can be relatively easily generalized. You find that, in fact, it's not hard to do this type of diagram for arbitrary loops. But some of them are not so simple. So perhaps there's some way to do this, perhaps not. At the very least, you can make arguments. For example, you can count how many wrapped diagrams are there at a given loop order, and because we expect the finite size corrections naively to be suppressed by lambda to the L, but also perhaps by an additional factor, and that factor might have to do with the number of wrapped diagrams versus the number of diagrams in general. And then, so this would be a very nice thing to be able to do in general. And then, of course, there's finding the next correction due to finite size. Well, okay, so what about loop 5 acting on the Kanishi operator or equivalent? Now you have a great deal more wrapped diagrams. So that's very far in the future. And that's what I wanted to say.
Thank you very much. Let me invite questions.
Yes?
When you say you calculated this good portion of your diagrams, you mean you subtracted all subdivergences?
Yes.
Really already clean.
Yes.
And for the next diagrams, do you have more of this work to subtract the divergences?
No, I started by calculating the 1, 2, and 3 loop diagrams that I would need and the counter terms. I have them in a file. They're done.
And you really don't need all of them, all the unwrapped diagrams to subtract this?
Well, you need, I mean, it's a large file.
Not all.
Basically you need all of the unwrapped diagrams of this type, the longest range diagrams for 1, 2, and 3 loops. And in fact, sometimes I end up calculating them twice or 3 times because when you come to the for loop calculation, you want to choose your incoming momenta to make your diagram maximally easy. And sometimes I chose poorly the first time. And then, of course, I calculated the 3 loop diagram equivalent to that. And I have to go back and recalculate the 3 loop diagram when I find the more appropriate choice. But in general, those lower diagrams are already done. Yes?
Is there any way to test integrability once wrapping interactions are included from your approach?
I think that I don't see how far the Kanishi operator, because really it's a 2 by 2 matrix.
Yeah.
And yes, we can diagonalize a 2 by 2 matrix. It's not hard.
But in principle, the extension of this. Right.
I think that if you could do the arbitrary length, you might be able to address that question more directly.
This planar diagrams?
Yes?
This planar diagrams you put on a cylinder or arbitrary?
What do you mean? They're wrapped, so yeah, they're on a cylinder. You could also think of them, if I go back to this one, you can draw them on a cylinder, but you can also draw them sort of in a more traditional way on a plane with an operator insertion. I'm not really sure what's happening.
Is the set of wrapping diagram is H invariant? What about H invariant?
I think the diagrams I'm calculating are.
Yes, sure.
So
when I talk to people who do for-loop calculations or free-loop calculations or high-loop calculations, they often make statements like 95% of the diagrams can be done in 5% of the time. So, how do you think this will be a problem for your calculation?
I think, let me see. There's one here, and I think it's this one. And also the same one with that first, with this third letter replaced by a gluon. They're essentially equivalently difficult. Those two diagrams are going to present a problem basically because when you reduce them down, you're going to get terms proportional to two-loop master integrals that need to be expanded out to really a large number of factors of epsilon. So those two could prove difficult. Basically, it's this diagram and this diagram, but I need them out to factor epsilon squared, epsilon cubed, and that can be done numerically, but getting matching to, it's fairly easy to match, you know, the first couple of terms to look at a numerical answer and say, well, I can see what the factor of zeta 3 in there is. Once you also have zeta 4 and zeta 5, it becomes more difficult to do that numerical matching. But these diagrams, so you know, I'm pretty sure I can get the final answer at least numerically, but there are a couple places where I think it's really going to be difficult to get those terms in terms of transcendental numbers.
And the other question I had is, if you can do 42 diagrams, can't you also do 400? I mean, just to be safe about everything.
I suppose, but I want to publish eventually. I mean, if you can make your life easier, why not?
Well, you should, definitely.
There's no reason to calculate all 433 diagrams. You can count, you know, if you can limit it down by a factor of 10, this is a good thing.
Okay, let's close now. We start again in half an hour's time at 3:30, so let's thank the speaker.